So I'm going to be talking today about running 3D in the browser. Try to avoid plugins because I really don't care for plugins. And now we can just run the 3D directly in the browser with WebGL and some of these other libraries on top of it. There are plenty of alternatives, but we really don't need to go there. So who's in this room? Hopefully mainly developers. If you are game developers, you should leave. If you're 3D artists, you should leave. I will explain why. Actually, I can give you a quick demonstration right now. This is my idea of a game. You try to get the ball into the hoop. You fiddle with the controls a little. And maybe you can do it if you're patient. There you go. We'll go through this. This is a little demo. We'll go through in a little more detail. But I also have a car. This is a car that I made. So this is why I'm not a 3D artist. Neither a game developer nor a 3D artist. But I dabble. I have fun. I can do what I need to do. So these are some exciting technologies for me. And I do end up using 3D from time to time on an actual project, not a game, clearly, not a virtual world, but I like this is a capability I've been waiting to have for a long time, and I do not like plugins. It all started with Flash and how you have to reboot your browser every other day because of some security bug and all this stuff, and they can't manage to get it working without restarting everything. But the other problem with plugins is getting people to use them. You put something out there on the internet and people go there and it doesn't work. And I got to install a plugin. And how many people do you lose right at that point? So I'm excited to do these things right in the browser. Forget about the plugins. People should visit. It should just work. Worst case, they might need a newer browser. I guess there's not much you can do about that. But some of the things that I've come across that use this are, I worked for a company that dealt with molecules, and when searching their catalog, you could do a molecular substructure search, and so you wanted to be able to visualize what you were searching for and the results you were getting. We've all been to sites that have products that just have pictures of the products. Well, ideally, rather than having a front and a back, it would be something, a full 3D image of the product that you could manipulate. In case they are showing you a picture of a cable and it's got 30 nice spools and you can't see the ends on it, so you don't know if it's going to plug into something, or a picture of shoes or whatever it is. Big data is popular now, but how useful is that data if you can't visualize it and interact with it in some way? And we actually, the last one on this list, we had a sales call with a company that builds custom parts for automobiles. And so the way they do it is they buy a new car, they take it apart, they run the parts through a 3D scanner, and then they know exactly how much space they have available for their enhanced parts and exactly what size and shape they need to be to mate with the rest of the car. So these are all technologies that I've really come across, and this is all stuff now that you can start talking about doing in the browser. Again, I'm not really personally that interested in virtual reality and games. You can do that kind of thing with these technologies if you're a better artist and programmer than me. So it's still useful for that. It's just not kind of my focus. So there was this VRML technology for building virtual worlds, and it has some of the same features you'll see here today, but it never really was native in the browser. You could go and see a demo with a plugin or something, or a special VRML browser. And it's still alive today, though you may not believe it. But nobody really seems to be using that. What we actually tried using for a while was Java 3D, which you could run in an applet. And it did work, and it had similar features and APIs to what we'll talk about today. But if you think installing the Flash plugin is bad, you should try installing Java 3D. You've got to get Java. You've got to get it working in the browser. You need DLLs installed. You need environment variables configured. You need the right graphics card, and so on and so forth. So it made some really nice looking demos, but the reality was it was virtually impossible to get anyone outside of your company to use it. What are the chances that they would have all this set up just right, or be willing to go through all that in order to view your site or your app? So there are other options. You can run 3D in Flash or in Silverlight. There are some other Java game libraries that have some 3D features that you can, again, run in an applet or in Java Web Start. The kind of the gorilla in the room is Unity, which is what the game developers use. It's a fancy environment that lets you build games and other things with 3D tooling. It works well with what 3D artists use. And at the end of it, you get a game or whatever that you can run in the browser with a plugin. You can run it on a tablet or on a console or whatever. So the game developers I talk to are like, just use Unity. They don't care about plugins, because if you want to play the game badly enough, you'll install the plugin, right? But I still feel like plugins are too much of a barrier to entry for anyone who wants to get at your app. So I'm trying to get away from all that. And the technology that's making it possible at the root of all this is WebGL. So there's some good news about WebGL. It is browser-independent 3D on the web. You can render 3D into a browser. It can be Firefox, Chrome, Safari, as long as you tick the right box. IE is now supporting it almost fully. Opera, even some mobile browsers. Nothing on iOS, but you can get it working on Android and BlackBerry. The Windows Phone developer release that just came out. So it's got reasonably wide support. You don't have to do any particular configuration or get plugins or anything. It is based on OpenGL, which most graphics cards these days support. It's very common. And itself, OpenGL includes a lot of features and extensions that then WebGL can take advantage of. So it's got a lot of promise. It renders into an HTML5 canvas. So you do need a browser that supports HTML5 and WebGL. But again, that's a pretty good list here and growing. Now, there's also not so good news, and that is that WebGL is very low level. And I'll show you an example. You'll see what I mean. And on top of that, you cannot just write a JavaScript program to display 3D. You need to write GL shader language programs that look a lot like C. You need at least 2 of them in order to put anything on the screen at all. So it's, we say it's 3D in the browser with, browser technologies, but really you need to, write your shader programs as well. It's not really just in browser technologies. And one of the downsides that, in particular, Microsoft griped a lot about was the security angle. You are compiling, linking, and running these GL shader language programs that you wrote within the browser, and they have direct access to your hardware, and they can do whatever they want. So, these things could do bad things to your computer, which is not a very happy thought. And the last thing on here is that you really can't work with WebGL without brushing up on your math a little. I kind of first look at this and say, oh yeah, I know what triangles are, and sines and cosines. I had that in high school. And it turns out when I try to do anything with it, I'm quite rusty. You need to be able to calculate, if something is a certain distance, what size should it be? If you want to rotate it in space, where does it end up? So that if you want to rotate it in space and then put it next to something else, where do you have to locate it so these 2 things look like they're touching and not, with a big gap in between? In order to get some of the right effects, calculating normals, which is if your surface is like this, what's the arrow that points perpendicular to it? So, it's kind of annoying to have to go through that all after, however many years it's been since high school and college when you may have studied this stuff. The only thing that really makes it possible is Wikipedia. So I guess it's a good thing that math has sufficient secondary sources that Wikipedia is allowed to talk about it. But what can WebGL do? Well, it can draw triangles. Now, this is the point in the presentation where I'm supposed to push the next button, and we're supposed to get another bullet point and another bullet point. But we're not really that lucky today. So seriously, what can it do? It can draw triangles very, very efficiently with a lot of features. They can be lighting and textured and shaded and bump mapped and so on and so on. Very fancy triangles, if you write the right shader programs to go with them. So this is really not what I'm looking for. So to be specific, what can it not do? It cannot draw a circle or a sphere or a cube or a cone or any other geometry that's more interesting than a triangle. You say, okay, that's fine. We'll draw them up in Maya or Blender, some 3D authoring tool. Well, I can't load models from those software packages. So you could maybe inspect the file format and tease it apart and figure out where the triangles and vertices are to put that in your code. But really, is that the best use of your time? Now, once you get the stuff into the scene, you draw it to WebGL, and then the next frame comes along, and you can't just say, okay, take that car I drew and move it 5 pixels to the right, because once you get a new frame, it's gone. It's a blank slate. So you have to remember where all your objects are and what all your objects are, and you have to handle moving them around as appropriate. Well, it also doesn't know about keyboard and mouse events. So you can't just say the W key should bring everything in the scene closer by 5 units. You have to handle the listeners, mouse listeners, keyboard listeners, handle moving the objects, and then telling WebGL about them all over again every time. And let's not forget that you can't do any of this if you're not writing these shader language programs. So it has all these wonderful capabilities, and you don't need a plugin, but you can't really write code for it either. So here's an example of some WebGL code. It starts out with a couple of shader programs. You need 2. And then we have a bunch of code here. It's not very visible, but it's OK. You're not missing much. A bunch of code to set up the shaders, to load them out of the DOM and link them and compile them. We've got, in the very dim text there's a whole bunch of vertices. It's just points, 0.8, 0.0, minus 0.6. And then I scroll down more, and there's another set. And I scroll down more, and another set, and another set, and another set. And a bunch of cryptic method calls like vertex attribute 4f, bind buffer, vertex attrib pointer, enable vertex attrib. Well, anyway, it's ugly. It's not, you're writing it over and over again. It's not stuff you should have to be writing over and over again. And what it gives you at the end of the day is this. So 250 lines. I have nothing in 3D. I have a few triangles and a hexagon. About the only nice thing on here is the coloring in that one triangle. And that is not very complicated at all, because all it does is assign a color to each of the 3 vertices, and then the shader program just kind of interpolates and says, if a point is equidistant, I'll mix the colors, and that's the color of this point. And you get the colored triangle. So that's a lot of code to write not very much. So that's why I don't find WebGL itself all that attractive. It is 100% of the infrastructure you need to put a nice library on top of, but you should not write code for it. Really, you should not write code for it. Now, there are a few things that you're going to need to know. The first is how the axes are set up, because this stuff is going to leak through to whatever library you're going to use on top of WebGL. So the right-hand rule is that if you hold up your right hand, the x-axis is your thumb, the y-axis is your pointer finger, and the z-axis is your middle finger. And kind of by convention, the z-axis points toward you, and the x-axis points to the right. But it sort of doesn't matter, because it all depends on where you're looking at the scene from. So this could be really pointing in any direction, and you can kind of arrange it how you like. But that's the right-hand rule. It doesn't, if you try to do it with your left hand, things won't work like they do on the screen. You have to use your right hand. There are various buffers that your graphics card uses, and therefore WebGL is aware of, and you might see this in the APIs you deal with, particular methods to clear these buffers. The color buffer is what color each pixel that's going to end up on your screen is. The stencil buffer controls what part of the screen you're actually drawing to. You can put in kind of weird shapes there to block out some parts of the screen and only draw to the rest. The depth buffer is, if you colored a pixel at a particular location, how far away was the object that gave you that pixel, so that if you end up with a closer object later, You can decide, do I then replace the color I had because there's something in front of it, or is it transparent and I need to kind of blend them together or whatever. There are two kinds of shaders. I mentioned the vertex shader controls the geometry of your vertices, and the fragment shader generally controls the colors that you end up emitting. And then there's scissors, which is a rectangle that controls, again, gives you another way to draw to only a particular subset of the screen. But probably, even if you see these terms, you can kind of ignore them largely, but you have to know at least about the axes. Let's take that and let's leave the rest of this WebGL behind. So what do you then run on top of it? There was a lot of buzz about asm.js, and the reason there was a lot of buzz is because they took an actual desktop game engine, the Unreal game engine, and ran it in the browser, and it ran well. This was a first-person shooter type thing if you're not familiar with it. So suddenly their press releases say, holy cow, we can run desktop games in the browser, which sounds great. So what is asm.js? It is a subset of JavaScript, and we'll see in a minute what that really means. But it's limiting how much JavaScript you use, and we've had talks here before about JavaScript, the good parts. Well, you're taking out the bad parts. You're only keeping the parts that perform well. It'll use WebGL for 3D. It will run in any environment that runs JavaScript, so any browser. Now, some browsers can particularly notice these asm.js programs and make them even faster, sending them straight to machine code instead of through an interpreter or whatever. And there are some tools around asm.js. The bottom line is it runs very quickly, up to 5 or 10 times faster than the same JavaScript code if you wrote it in normal JavaScript and your browser didn't recognize it. So, it sounds very promising. So what does asm.js code look like? Well, it looks kind of like this. So, you read all those press releases and you think, wow, this sounds really cool. And then you look at it and you're like, holy Christ, what's left? Some of the things, in this subset that you don't have access to are, for example, strings and objects and anything that's not a number. Dynamic typing is gone. Everything's a number. You get a lot of these little bars where you're casting things into different kinds of numbers. So it's really not something you write by hand. Instead, you write C or C++ code like they did for the Unreal Engine, and then you use this tool to emit this incredibly obtuse-looking JavaScript, and it runs really fast. Okay, that's great. But again, not something that is really that interesting to try to write an application in. So there's a lot of game stuff you can use. Again, I mentioned Unity. One of the neat things about Unity is they sort of recognize that people don't like plugins that much. And later this year, their next release is going to have experimental support for just emitting directly to JavaScript and WebGL, which is fantastic, but I don't really know what experimental means. I don't know how long it's going to be before that is actually something that works well in the browser and is reliable and people actually deploy it. So we'll have to see. That has some promise. Again, there are these Java game engines, and when WebGL first started showing up in browsers, a lot of people suddenly threw together a WebGL game engine or a JavaScript over WebGL library. And the problem is that if you look at those today, a lot of them, the last update was in 2012 or 2010, and they say, oh, we've got a new release coming. And, that was a couple years ago, and that's the last you heard. Or you can just throw the web out. Well, none of these are that attractive to me either. So I think a better way to go is there is one JavaScript over WebGL library that's still alive and kicking, and that's THREE.JS. So that's what I'm going to spend a lot of the rest of this talk looking at, THREE.JS and how you can do things using the APIs it provides, and it gives you a much more sensible way to work with WebGL. So THREE.JS is actually used in practice. It does fill in a lot of the gaps of WebGL. It has a lot of those features that WebGL doesn't. It sits on top of WebGL just in the way we'd want it to. It is still under development, so if you poke around a little, you'll see docs that say to do, and you'll find some bugs in the file importers and exporters and things. But there are a lot of people using it. There are a lot of examples. This is the home page of it, and every time you load it, it has a different set. And each one of these tiles is a cool application that someone has written in WebGL. So let's see if we can get a good enough connection to actually run one of these demos. I guess it's taking a little time to load. It recommends headphones. But it hasn't. Well, we'll give it a minute to load. There are people out there using it. It is being actively developed. The one, if you look at it from a gamer perspective, you'll say, a game developer perspective, you'll say there are no tools there. Where's my 3D authoring tool? Where's my tool for defining, in some sort of visual environment, how different things react to different kinds of inputs? And that's not what it is. It's a developer level tool. I guess this is run. This is ready to go now. So this is an example of how I can poorly play a game that was written in WebGL. I think the point of this is to dodge these glowing walls. So this is just running in my browser. Oop, there we go again. I'll spare you my gaming skill. But at the end of the day, it's not really as capable as a desktop 3D first-person shooter type game, but we're getting there, and there's a lot of cool stuff you can do. So one of the things that WebGL didn't do that THREE.js does do is track all the objects in your 3D environment. So you can set up a scene and add things to that scene, and it will remember them, and then later you can just say, okay, please take this one and move it over, or change the color, or whatever you want to do. It can render that to a web page. We'll be talking about the WebGL renderer. If you don't have WebGL available, it can do ASCII art or render to a canvas or some other things. But the main way to use it of interest is rendering to WebGL in the browser. And then the thing you'll see as we go through this is the typical way you operate is to create what's called a mesh, and a mesh combines geometry and appearance. So it may be the geometry of a sphere, and it may have a wireframe appearance, or it may have a solid appearance, or it may have a texture applied, so it looks like the Earth. It may be shiny or dull or whatever. So the concept of a mesh is you take the geometry and appearance together, and that's something that lives in your 3D environment, something you can add to the scene. So the code to set up a THREE.js scene is a lot more straightforward than the WebGL scene. You create a scene object, you create a renderer object, you set the background color, and you, in this case, tell it to take over the whole screen, to render to the whole browser window, rather. And that's it for the setup. So the first thing you're going to want, other than some objects, is going to be some lighting, because you want the objects to be visible. You may, if they're going to reflect or shine, you need to know which direction the light is coming from. If they're going to create shadows, you need to know where those shadows should end up. So the different materials react to light in different ways, but you start by positioning lights, deciding whether you want shadows there. The shadows turn out to be a little expensive computationally, so if you can identify objects that don't need to create them or don't need to receive them, you can give yourself a little performance boost. But as long as you have a surface on the ground that's willing to receive shadows and an object that's willing to cast shadows, then your light can make that all work. So there are different kinds of lights, but typically you have some ambient light that's just sort of a background there, and then softens the shadows a little, and then you have spotlights, which are shining from a certain direction to light the objects and create the shadows. So not a lot of code. We've got two different lights here and not a lot of code. Then you need a camera, which is the way you're going to view the scene. So the position of the camera determines which angle on the scene you're going to see in your browser. When you render it, you show the view from the camera. So if you want to move through this environment, you can either move all the objects, or you can just move the camera around while keeping the objects stationary. And there are different styles of cameras as well. I mean, I'm only kind of scratching the surface of all the things that you can do with WebGL and THREE.JS, but I just want to give you sort of the high-level view of the kind of things you can do. One of the cameras will give you sort of a SimCity-style view where no matter how close or far a building is, it looks like the same size. So you see one big grid. Or it can be a normal perspective camera where the farther away something is, the smaller it looks. And again, I mentioned the right-hand rule for the axes, but depending on where you position the camera around those axes, they may appear on the screen some totally different way. So we'll talk later about some helpers to make some of these things clearer. But again, the camera code is not that elaborate. You instantiate a camera, you set some properties for how wide its field of view should be and whether it should ignore objects past a certain point. Give it a position, point at it, tell it where it should be looking, add it to the scene, and there you go. And then you can then animate the objects in your scene, either, again, by moving the camera around or moving the objects around. And typically, the way a THREE.js program works is you have a render function that you call every time you want to display a frame to the browser. And you can use an API called request animation frame that's sort of a more recent addition to ask the browser to give you a call back when it's time for the next frame to go out there. So it's superior to set timeout and set interval in the way you might have done kind of a timing mechanism before, because the browser has slightly more sophisticated logic. It will target 60 frames per second, which is what people typically use on LCD monitors. It will pause when a tab is hidden. So if I start up one of these examples, and I've got on the top left corner, there's a little graph of the frames. So I switch back to the presentation. I'll go back there in a minute, and you'll see that it hasn't been running while we've been in a different tab. So it saves energy, saves your fan from spinning up when it's not needed. So the basic structure of many of these apps is you have a render function that calls request animation frame at the end to call the render function again, and you end up getting this render function called every 1/60th of a second or so. And then the job of that render function is to adjust the camera position, the object position, or make whatever changes you want to make, and then tell THREE.js, please render this. So here's a render function. The first thing it does is try to calculate exactly how much time has passed since the last time it was called. I mean, there could be reasons, why it is not exactly 1/60th of a second. And if you have an object moving across the screen, you would like it to move at a fairly consistent pace. You don't want it to stop moving when the computer slows down for some reason and then leap ahead all of a sudden. So the top few lines there are just trying to calculate exactly the right pace for moving things to move based on exactly how much time has passed. Then adjust the positions of a few objects and render the scene again, and then call request animation frame just to keep the cycle going. So this is very typical of the actual meat of a render function. Now I mentioned there are some helpers that'll make this a little easier on you. So up here, there's the frame rate helper in the top left, and you can see the little gap in the graph while I was switched to a different tab, so it wasn't actually running this whole time. On the right, we have these little control widgets, and one of the reasons is if you take a scene like this and you first set it up, maybe your light is too bright, and it's hard to tell what the actual shape is, or maybe your camera angle is wrong, and you're right up next to it, and you can't tell that it actually goes back at all. It just looks, you're just seeing the side of it. And it turns out to be surprisingly difficult to get everything right the first time without doing some tweaking. So it's nice to have a little tool like this that lets you, lay out a scene and then start tweaking it and figuring out what are the right values to then go put in your code. So there are little JavaScript libraries for both of those. Stats.js has the frame rate display. Dat.GUI has that little GUI for making little adjustments. And that makes it a lot easier to just get things just right. There are different helpers that THREE.JS includes. You can have one to show the axes and whatever orientation they might be at the time. You can have one for a light that shows like the outline of where's that light shining. You can have one that turns everything into a wireframe, so if something's not visible and you don't understand why, you can take the materials out of the equation or whatever might be causing the problem and just say, I want a red wireframe. Please let me see what's going on here. Plus, you have all the normal JavaScript developing tools, debuggers, you've got the console output and all that kind of stuff. So these are some of the tools you might use as you're playing around with this. And the setup, again, is not that elaborate. A few lines to set up the stats and put them wherever you want them on the screen. Then I have a little control object in the middle there where I just have properties that I want to be able to change. And then you tell the little GUI, these are the properties I care about. These are the acceptable ranges. And it'll put itself on the screen. And then in your render function, you just have one line to update the stats to notify them that a frame has been drawn so the stats can then put the right frames per second on the screen. So, you don't have to add a whole lot in order to get that customizability during development. So THREE.js comes with a lot more sophisticated geometry than WebGL. There are 2D shapes, rings, circles, planes, and arbitrary shapes. If you look at the car again, the right-hand side of this car facing us is a two-dimensional shape, and all I did was extrude it backwards and just say, please, make a wide 3D version of this thing and round the corners. So that shape was made with a THREE.js shape, and I can bring up some of the code for this that just says, make a spline through these points and a line and another line and another line, and okay, there we go. So you have a lot more flexibility. This under the covers is made up of a lot of triangles, and I guess in the other one here I have done too much. When my browser comes back to me. You can actually just tick a box in the controls to show objects as wireframes, and then that makes it a little easier again to see how the triangles have been applied and what the thing looks like without worrying about the lighting and positioning and some of the other effects. I might have to kill this. I guess that's the downside to running everything in your browser. Okay. So in order to create that 3D car, again, I took a 2D shape and just extruded it backward. You can also build cubes, cylinders, tubes, a torus. In the basketball example, the hoop was a torus. You can do 3D fonts, and in this example, I did not do that. This text that says WebGL basketball there is actually 2D, and it's not even in WebGL at all. It's in a HTML paragraph that I just rendered on top of the canvas, because it's not that efficient to define fonts in THREE.js, where essentially what you're doing is making a JavaScript definition of a font in order to then make a WebGL shape out of it using triangles and things like that. That turns out to be, again, not very efficient. And so if you're just displaying some text, it's easier to use your HTML widgets, which are very good at displaying text, and just overlay them onto the scene. But if you want that fancy 3D spinning text or whatever, you can do it. A lathe is if you imagine taking a shape and spinning it around one of its axes like you would mold clay or something like that. You can make shapes that way. An extrusion is what I did when you take some kind of existing shape and just say, draw it out this way. Okay, now I have a 3D version of it. And you can combine these. You can add and subtract and merge and things like that. So there's a lot more sophistication. But at the end of the day, you're still writing code to do this stuff. So if we look at a torus, for instance, I'm writing code that tells the radius of the whole thing, the radius of the tube, the number of individual segments to use, which in other words, how many triangles to break it into. Then, setting up a material for it, which I don't go into yet. But then, once you have this mesh with the geometry and the material, you can position it around the scene. You can rotate it. You can stretch it or position it or rotate it any way you like to get it in exactly the right place. So this is just a few lines of code that ends up making hundreds of triangles on the screen, and it looks good and performs well. So that's kind of neat. But again, my version of a car, which I did with a similar amount of code, is not that. It doesn't look much like what you go outside and get into to drive away at the end of the day. So there are some more sophisticated options. You can group things together either for performance or so you can move them and rotate them together and things like that. But it's not as convenient if you really have separate objects. So I wouldn't group the basketball and the hoop together just for performance because I want the basketball to be moving independently. But if you had a hoop and a backboard and a net and a pole and all these things, you might group those together just because they're always going to be acting together, and it'll save you the trouble of trying to update 5 things if you want to move them together. Now, aside from the objects, you can also have particles, which are you would think little dots, but something like that for rain, for snow. And rather than just being a dot, you can make it a cube or a sphere, or you can give it a texture so it's a little images for each one. So you could have a snowflake image for your snow or a raindrop image for your rain. You can take a 3D object and turn all the vertices into particles if you just want kind of a cool visual of it. And then slightly fancier than particles are sprites, which again if you imagine a billboard, a sprite is like a picture or a face, a 2-dimensional thing that's always facing you. So no matter which angle you look at it at, it's always facing you. It may be tied to a position in 3D space, so it may be something where it's in the middle of all the other objects in your scene, or it may be tied to a position on the screen. So it could be, your status display, around the borders of the screen or something like that. Though again, you could just do a regular 2-dimensional canvas to draw that stuff and not mix it up with your 3D objects, as long as you're in a browser anyway. So, there are different ways you can handle that. Then after we talk about geometry, we talk about the materials. So you can give something just a color and say, make it this color. You can have it vary by the distance from the camera. You can have it vary by the angle of the face, so that if you're trying to figure out what your geometry really looks like, you can color the faces differently depending on which way you're pointing. You can make it look dull or shiny or whatever. So all these things in the basketball game, the ball has a more dull material and the hoop has a more shiny material. And you can make it shiny like plasticky shiny or shiny like metallic shiny. Again, not a lot of code to set this up. You just give it some geometry and a color, maybe a couple of properties, and we've got the ball material on top and the shiny or hoop material on the bottom. And on top of that, you can apply textures, which are normally fairly intelligently applied. So if you have a picture of the Earth and you apply it to a sphere, you'll get something reasonable. It's not going to be completely accurate because usually the textures are square and the sphere does not, there's no reasonable way to apply a square texture to a sphere without distorting it somewhat. But you can understanding how that's done, you can create the right amount of stretching in your texture that you get a very accurate sort of representation when it gets mapped to the sphere. You can, you can control how textures are applied to the object, whether the whole texture is used or a subset, whether it should repeat itself or whether it should be stretched out. You can, have a text or image you provide and, make versions of it in different sizes. So the most accurate one for the size of your object is used. So, there's a lot of fancy things you can do with textures. Then on top of just the appearance you're applying to the object, you can use bump mapping and normal mapping and so on and so forth that will make it look bumpier than it really is. So if we wanted to, have a texture that included the little wrinkles in between the panels here, or the fact that this panel is not perfectly smooth, you can do that. A brick face or a stone face to a building, would have little bumps. And you can make it look kind of good with a bump map or really good with a normal map. The problem is the normal maps, you need special tools to produce. Light maps will let you kind of fake out shadows if you don't want to incur the calculation of shadows on every frame, but you have an object and you sort of know that it's going to stay in one position. You can fake out, you can just kind of have a static shadow sitting there with a light map. You can have reflections or translucent objects with environment maps, objects that have different amounts of shininess on different parts of the objects with specular maps. So these are all these, I don't even have an example of every single one, but there's a lot of fancy stuff you can do with the features that are in there. So it doesn't take you very long to say, I shouldn't be writing this code by hand. To create these objects, to create these materials, to align the materials on the objects. There are tools for this, and there are. An open source one is Blender. You can go download that right now, Windows, Mac, Linux. You can start creating objects and models that you can then export either in a JSON format that THREE.JS supports directly, that's kind of its native format, or in one of a variety of more common 3D interchange formats that THREE.JS would understand and be able to load from. Now on top of that, it supports formats like the formats used commonly by 3D scanners, by 3D printers, by the Protein Data Bank, and there are other options. You can get formats for Oculus Rift and different things like that. So, some of this stuff is pretty neat. I haven't played with it at all yet, but the thing I've run into is it's not as straightforward as you'd like. You can just go download a model off the internet and load it into Three.js, and it might, it might have invisible parts, or the materials might not work right, or some of the internal arrays may have the wrong values, and so it mostly renders, but you get some error messages that aren't very helpful when you try to load it, or it's incredibly detailed and the whole frame rate slows down every time you try to include it in your scene. So it's not idiot-proof. I think the problem is that a lot of the models you'll find out on the internet are made to look really good, and what you want to display in an actual application is something that's much more simplified and looks pretty good, not really good. So it's kind of a trick to get exactly the right stuff to load. And I'll show you a couple of examples. This was the first car I went to try to open up in Three.js. I went searching for car models. I found this. I thought, wow, this looks fantastic. And this is just an image of it because I loaded it in Blender. I exported it to a JSON file for Three.js. And that JSON file was 65 megabytes. That's a lot of JSON. And I tried to load it up in the browser, just disappeared, gone. Didn't even lock up, it was just gone. So that didn't work too well. So then I tried the Ghostbusters car, which is a simpler model. And that came out okay. I mean, you can kind of see it. It's got some, it looks sort of like the crazy thing they drove around. But the problem is the stuff on top is like dark no matter what you do. So something's going on with the materials in some of those things on top, and they're just not coming out right. I mean, you can see some of the stuff appears correct. You can see the red tail fin very clearly. And you can see, if I turn the brightness up enough, you can see a little gray box there, but there's other stuff that just shows up black. So, clearly there's detail there. I don't know why it's not showing up. So that would need some debugging to figure out, what's really going on there. So, it's not as straightforward as you'd hope, but, if you work with somebody, you can get past this. I have a protein example. You can download and load a protein from the protein data bank. It's very nice, but proteins turn out to have kind of a lot of atoms, and the browser gets a little cranky. So, random models don't work that well, but actual apps look really good. So the key is finding those nice things on the internet and maybe working a little more closely with someone to get, the kind of models with the kind of level of detail and the kind of textures you're looking for. So just a quick example of the code to import a model. It's, again, there's not much there. So you instantiate a loader, point it at some files. It's going to give you a callback. So you might do things like, this is for the Ghostbusters car. It came on a plane by itself, so there was a big black area, and I wanted to take that out. It was very small compared to what I wanted it to be, so I increased the scale of it. Simple things. And add it in, and it works mostly. So, you can do these things without a lot of code again, but, getting the right model is the trick, not getting the right code. Now, once you have a scene set up in THREE.JS, you can export it to its JSON format to load later if you want to, bring it back up again, either to local storage or send it to a server or whatever. One of the things I haven't tried but would like to is you can export it to a model for a 3D printer. So that would be pretty cool to manipulate things in a THREE.js app and then click a button and say, okay, I'd like to print this now, and walk over a few minutes later and get your plastic model in real life. So that's something I'm excited to try, but I haven't yet. And then I mentioned earlier the issue with controls. The controls are, the keyboard and mouse controls you're going to use to interact with this scene. And, typically you think of them moving objects around, but really they might be moving the camera around. But THREE.js includes controls appropriate to flying, appropriate to first-person shooters, appropriate to Oculus Rift, the 3D headset you can wear, appropriate to, orbiting around something where you want to be sort of facing the same thing but just moving yourself around it, and so on and so forth. There are other controls. The catch, being in a web browser, is that you can move your mouse right on out of the window. So you can move it to the edge of the screen and bump it against the screen, and then no matter how much you move it over, you can't turn that direction anymore. Or you can move it out of the window, and suddenly you're not interacting with the app at all anymore. So there is a spec coming down the pike called pointer lock, which will allow you to allow the browser to capture your mouse and not let it out, and then it can handle the mouse controls completely. You get the little pop-up. I don't know if you noticed it earlier. It asked when I went into that game if I'd be willing to allow it to capture my mouse, and then you can hit the escape key to get out of that. I guess this is going to have to load up again before I can show that. But it's a draft spec. It's supported in Chrome. In Firefox, when I tried it, it worked, but it forced the application to run full screen in order to work. So that in Chrome, it was just willing to work as is. So it depends a little bit right now. It's still evolving. It's just a draft. So hopefully, that'll come around before too long, and that'll really let you have the kind of controls you would have in a desktop app. And one last thing is, if you're not locking the pointer, if you're actually letting someone move the mouse around, you can figure out what object in 3D space their mouse is pointing to. So you can let them select things and interact with things in that way, which is kind of neat. And again, there's so much more to it, what you can do, but hopefully this gives you sort of an idea of the sorts of things you can do, and the fact that using THREE.JS, there's not that much code compared to what you do using WebGL or something like that. So it cuts down on the code a lot. It gives you some very useful abstractions and features, but probably at the end of the day, you'll want a partner who can do some of the modeling stuff at least. But this is the complete code example of the basketball game. The first block sets up the statistics, the frame rate display. We set up the basic THREE.js items in the scene. I have 3 different meshes, one for the plane on this black rectangle that everything's taking place on, one for the basketball, one for the hoop, the lights, the camera. The biggest block in here is for the controls, because I've got a number of controls in this little window, and when you change the appearance of the basketball, you can actually, I've got one in here where you can show the underlying geometry there, rather than, oh, you can't see it that well on the screen. When in the lighter parts, you can sort of see when it bounces towards us, you can see it's made up of squares where it used to be smoother, each of those squares being 2 triangles. Let me see if I can bring it any closer to this. Spends a little more time in the light there. So you can see it's got the facings are a little clear. If I make it smooth, it has that more rounded appearance. So that is a decent chunk of this code, just setting up the switching between the facings or the smooth. And then the render function is pretty small. Again, it calculates the timing, adjusts the position, and then requests that you get another frame shortly. So it's less than half the code of the WebGL example for a lot more functionality. So the bottom line is THREE.js really makes WebGL more usable, I think, as a developer, as an application developer. It gives you a lot more options. But you still have a decent amount to wrap your head around. And there's nothing it does that'll make you a good artist. So again, this is where you want a friend. But if you want to poke around a little more, again, the THREE.js website has all those real application examples. They also have an examples directory with a lot of individual examples of specific features that you can browse around with and view the source for. So you can learn a lot that way. So I guess in summary, it is now possible to do 3D in the browser. Just because WebGL is there doesn't mean you want to use it, and just because you hear about asm.js doesn't mean you want to use it, but a library like THREE.js, I think, is much more usable. And if Unity arrives with native support for JavaScript and WebGL, that'll be, I think, very exciting, because it has a lot of the sort of game developer tools, graphical tools, an authoring environment, plus the ability to then leverage other platforms to export to a console game or whatever the case may be. So that's very interesting, but again, it's in the future somewhere. And I did actually show some of my code once to a graphical artist, and he kind of looked at it, and his first reaction was like, oh, it's code. What is that really doing? And so I explained, that these were vertices and lines, and this is how I'm defining a path. And he sort of got this look of horror on his face, like, you mean you wrote pages and pages for that? You spent your time on that? Why don't you just use Maya? Well, because it's $3,000. I need to get better at Blender. I think that would be a lot more efficient than if you look at the code for my car, I've got this big block here defining just tires of the car, and up here I'm defining the shape of the body. This is the stuff that terrifies actual artists. So you need more tools if you're really going to go somewhere with this, I think, than just, Three.js is a fine library, but you need a stack of tools, not just this one. So keep that in mind. And that's what I have. So I'll be happy to take any questions. All right, well, I'll be around for the rest of today and tomorrow, so feel free to grab me in the hall if you want to talk.